Hey guys, welcome back to the channel. If it's your first time here, we go through math and physics tutorials, as well as how to improve the mindset of a student. In this video, we're going over reciprocal functions and rational functions. I'll be going through the difference between these two functions, as well as how to find the vertical, horizontal, and oblique asymptotes. By the end of this video, you'll be able to graph both reciprocal and rational functions using asymptotes, intercepts, and values approaching from the left and the right. If you find this video helpful, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. At the end of this video, we'll talk about how a disorganized desk or desktop actually leads to poor cognitive performance when compared to an organized space. Alright, before we go over what the difference between a reciprocal or a rational function is, I want to go over some terms that we're going to need to know before we start diving into those definitions. So here we have a vertical asymptote, and that really refers to a vertical line on a function or on a Cartesian plane that a function approaches but never touches. So that's important right there. It actually never touches this point, but it goes to that point. This is also known as an infinite discontinuity. Next, we have a horizontal asymptote, and this is very similar. It's a horizontal line a function approaches but never touches. And this can also be known as end behaviors of a horizontal asymptote, or end behaviors of the function. And finally, we have an oblique asymptote, and this is a line with a slope. So in the vertical and horizontal, they don't really have a slope. Like their values are either x equal to a constant or y equal to a constant, and that's the equation of a line. Whereas here, an oblique asymptote, we have a line that is represented by y equals mx plus b, so there actually is a slope. And again, it's the function approaches this line but never actually touches it. Lastly, we have a hole, and that's a point where the function is undefined at, and this is also known as a point discontinuity. Alright, so now we'll go into kind of the definition of a reciprocal function, and if those terms didn't really make sense, I think it'll be a lot more clear as we go through with the examples, so don't worry. Here we're going to go through a reciprocal function, and this basically takes on the form y is equal to the function, and it's going to be a over x minus h, and then plus k. So this is the general form. Again, these variables, it'll be a lot more clear when we go through an example, but it's basically a constant divided by a polynomial. That's how I think of it, and that's how I think you should think of it. So here, if we scroll down, a reciprocal function is really just a function that's the inverse of it, or the reciprocal of it. So here we have an original function like y equals to x, or f of x equals to x, and the reciprocal function is going to be 1 over that function. So here we have the graph f of x is equal to x, and obviously that's just a straight line. And then in the blue we have r of x, and that's equal to 1 over x. So the reason I bring this up, I want to show you kind of the similar characteristics between the original function, which is the line, and the reciprocal function. So if we look at some of these similar characteristics and look at this graph, we have the same positive and negative interval. So that means that wherever the graph of f of x is equal to x, so the line, is positive, which is in this area right here, in this quadrant, the reciprocal function is also going to be positive. So this blue line here is actually always positive in this area. So they're positive intervals, so they're the same. We also have the negative intervals, so if we look over here, wherever the function f of x is equal to x is negative, that's actually the same negative interval of the reciprocal function. So next we have the y-intercept of the original function will be the reciprocal of the y-coordinate of the reciprocal function. So basically what that means is if we have an original function with a y-intercept of 0, 2, then the reciprocal functions, the RCP, the reciprocal function's y-intercept is going to be 0, 1/2. So it's the reciprocal of that 2. 2 over 1, the reciprocal of that is 1 over 2. So next we have the reciprocal function has an asymptote at 0 of the original function. So here, the original function, if I do this in green, the original function has a 0 at the origin. And that actually ends up being the asymptote of the reciprocal function. Lastly, we have the opposite decreasing and increasing intervals from the original function. So what that means is here we have an increasing function in our original function, right? It's a positive slope. So as y gets larger in the positive direction, x gets larger in the positive direction. So that stays positive. Here, it's going to be the opposite of that for the reciprocal function. And I think you can see that this function here has a slope that's actually negative. As we go further in the x direction, y is decreasing. So that means it's going to be a negative slope. And then similarly, over here, we also have a decreasing interval. So that's the only kind of opposite situation where from the original function to the reciprocal function. we have opposite, decreasing, and increasing intervals from the original function. Okay, now we have another reciprocal function where the original function is y, or f of x, is equal to x squared, and the reciprocal is going to be 1 over x squared. So in this situation, all of the characteristics are still the same in terms of how they match up to the original function. So again, same positive and negative intervals. So with a quadratic function, there actually is no negative intervals. Nothing passes below the x-axis. So this is positive all the way over here in these two quadrants. And the reciprocal function is also positive in that area. And I won't go through all of these, but I'll go through the last one where we have the opposite, decreasing, and increasing intervals from the function. So for this quadratic, we actually have a change. So we have a decreasing interval in the quadrant 2 over here, and then we have an increasing interval. So the reciprocal function is going to be the opposite of that. So in quadrant 2, the reciprocal function is increasing during that interval, and in quadrant 1, it's decreasing that interval. So again, it kind of matches up that the original function is going to have opposite intervals for increasing and decreasing compared to the reciprocal function. All right, so now kind of the last definition before we get into problems and like the strategy for solving or graphing rational and reciprocal functions. Here is the definition of a rational function. It's basically f of x is equal to p of x over q of x, where p of x and q of x are both polynomials. And so here's going to be where we go over the strategy for how to graph both reciprocal and rational functions. And these steps can be kind of applied to every single problem, both reciprocal or rational, and get you kind of the right answer and get you on the right track. So first, we're going to factor the numerator and denominator if possible. Sometimes it's not, but we're always going to try. Number 2, we're going to check for the vertical asymptotes. So that's where the function is not defined. And we're looking for that vertical line that the function approaches but never touches. We're also then going to go for horizontal asymptotes or oblique asymptotes. So again, that horizontal line that the function never touches, or that sloped line that the function never touches. Then we're going to look for y-intercepts and x-intercepts if possible. Not all of them have them. And finally, we're going to go over the value from the left of the vertical asymptote and from the right of the vertical asymptote. All right, so for our first problem, we have something that says graph the function, and we're given 5 divided by x squared plus x minus 6. So here, I know this is a reciprocal function, and I know that because it's a constant, so this constant on top, divided by a polynomial. So looking at our strategy, we're going to kind of follow it. We're going to follow it in order. So we're going to look at the first step, which is factor the numerator and denominator. Well, the numerator can't be factored. It's already in its simplest form, but the denominator can. So I'm going to say we need a number or numbers that their product is -6 and they sum to +1. So that's going to be +3 and -2. So 3 times -2, that's -6. 3 plus -2, that's going to be 1. So now we factor this. Now we can go on to step number 2, which is the vertical asymptotes. So vertical asymptotes are an infinite discontinuity. That's what they're also known as. And they're basically where the function is not defined. So we're trying to find where the denominator equals 0. So in this situation, it's very similar to like having a quadratic and finding the zeros of the function. It just happens to be in the denominator. So here, if I put in values of x is equal to -3, this term here would be 0. And therefore the whole function would be divided by 0 and undefined. So we're going to have one vertical asymptote, so I can write VA. One of them is going to be at x equal to -3, and the other one, if I do x is equal to 2, then this area is going to be 2, and the full function is going to be divided by 0. So the other one is going to be at x is equal to 2. Now, once you've done this step, so this is step number 2 right here, I want you to right away graph these vertical asymptotes. So we have -3 and 2. So I'm going to graph them like this, and I'm just going to put a line. So that's going to be -3, and we're going to have 2 right here. So this is x is equal to -3, and x is equal to 2. All right, so now we're going to look at the horizontal asymptotes. So for horizontal asymptotes, what we're doing is we're taking the ratio of the leading coefficient of the numerator and the denominator. So in this situation, I'm going to rewrite the function as f of x is equal to 0x squared plus 5. And then I'm going to go back to our original form where it's x squared plus x minus 6. And so when I say the ratio of the leading coefficient, from the numerator to the denominator, what I'm saying is I want to find the value of, well, this will be our leading coefficient for the numerator, so it'll be 0, and then our leading coefficient for the denominator would be 1, because there's going to be a 1 right here. So it'll be 0 over 1. And this is just to show you that this strategy or these steps apply to all of them, because we're going to see a little bit later, we're going to see that sometimes this coefficient here is actually not 0, and so the horizontal asymptote actually has a value. But in this case, we have a horizontal asymptote where y is equal to 0. And just like step number 2, I want you to graph that right away. So if we go to our graph, I'm going to graph our line of our horizontal asymptote, and that is at y is equal to 0. So at this point, we've kind of like sectioned off the Cartesian plane or the xy plane, and what we're saying is we have these lines that our function can't touch, but it's going to approach. That's the definition of a vertical or horizontal asymptote. So that's going to be very valuable later. But let's keep going, and let's go on to strategy number 4, step number 4. So step number 4, find the x and y-intercepts if possible. Okay, so I'll start with the y-intercept. So this is where we just take the function and we set x to equal 0. So it's going to be x plus 3 and then x minus 2. So if I just put in f of 0, I'll get 3 in the denominator multiplied by negative 2. So I'll get a point. So f comma 0 is going to be 5 over negative 6. So I have a y-intercept at 0 comma negative 5 over 6. So now we can graph that y-intercept point. So 0 comma negative 5 over 6. That's probably going to be right around there. That is our point here. I'll put it above. 0 comma negative 5 over 6 is that point. And so now we're going to check for x-intercepts. And for a step, there's a few steps here where we're only do them if it's possible. And so an x-intercept, that's defined when the y value is equal to 0, or the function is going to pass through the x-axis. Here we have a horizontal asymptote at y equals 0, or the x-axis. So we actually aren't going to have an x-intercept because it can't pass through there. Again, this horizontal asymptote is a line the function approaches but never touches. So I'll write for our x-intercept does not exist. And so there's one part of this graph where we can actually solve, or like part of the graph where we can actually graph it. So because we have a vertical asymptote at x is equal to negative 3 and x is equal to 2, as well, we have this point here. The function wouldn't be able to go up like this because then it would be passing through this horizontal asymptote. So it's actually, it has to kind of go down and also go through this point. So the function has to look like something like this, because it has to go through that point and it's not going to ever touch these vertical asymptotes. Alright, so lastly we have step number 5, and this is from the left or the right of the vertical asymptote. So I'm going to do f of x is equal to 5 over x plus 3 multiplied by x minus 2. And here we're basically looking to see if the function exists in this area or this area on this side, and this area or this area on the other side. So when we say from the left, what that means is going to be from the left side of the vertical asymptote. So here we can't put in the value of x is equal to negative 3, but we can put a value from the left of that. So we can put in like a value of x equal to negative 4. And so that's what we'll do. We'll start off with f is equal to negative, or x is equal to negative 4, and then we'll have 5. This is negative 4 plus 3. This is negative 4 minus 2, and we're going to get a value that's 5 divided by negative 1 times negative 6. So we're going to get a positive value at negative 4. We're going to get 5 over 6. So we have a point at negative 4, 5 over 6. So now that we know, that it's positive, it's going to be negative 4, it's going to be right around there. So now, because we have these asymptotes, we can draw the function, and we know it's going to be looking like something like that. Because it's going to go through this point, and it can't touch the horizontal asymptote or the vertical asymptote. Finally, we're going to look at the right of x equals to 2, because we've already defined the graph from in this area, but we haven't defined it over here. So now we're going to put in a value that's to the right of x equals 2, so we can put in a value of 3. So if we put in a value of f of 3, it's going to equal 5 over 3 plus 3, and then it's going to be 3 minus 2. So here we're going to get 5 over 6 times 1. Again, we're going to get a point of 3, 5 over 6, just like in the other side. So it's again going to be right here. And then now we have our function defined from this section of the graph. Alright, so for problem number 2, we actually now have a rational function. And it's a rational function because we have a polynomial in the numerator, so here, and in the denominator. So these are both polynomials. But because we have this strategy, we can kind of just run through the exact same process and see what we get. So for this first section, or first step, we're going to factor. So here we could do a GCF of the top, and then also of the bottom. So 3 and then x plus 2. And then now we're going to go to step 2, and we're going to check for the vertical asymptote. So again, this is where the denominator is equal to 0. So what x values make the denominator equal to 0? Here, it's going to be x is equal to negative 2. Because negative 2 plus 2, that's going to be 0 in the denominator, and that defines where the function will be undefined. So here, we can draw our x is equal to negative 2, vertical asymptote. Okay. Now we can go to strategy, or step number 3, where we're finding the horizontal asymptote or the oblique asymptote. So for a horizontal asymptote, we look for the leading coefficient of the highest degree term in the numerator and the denominator. So here, the highest degree term, well, both of the numerator and the denominator are x to the power of 1. And then we're going to look at the leading coefficients of both of those. So that's 5 and 3. So 5 divided by 3, that's our horizontal asymptote. So now that we have our horizontal asymptote of 5 over 3, we can write that as an equation of a line of y is equal to 5 over 3. And then we can graph that. So that's going to be this right here. We're going to have y is equal to 5 over 3, and that's our horizontal asymptote. Next, we can check the y-intercepts or x-intercepts if possible. So here, let's put in our x-intercepts. So let's do f, where x is equal to 0. It's going to be 5, 0 minus 3, and then 3 times 0 plus 2. So we're going to get a value of negative 15 on top, and then 6 on the bottom. So we can reduce this negative 15 over 6. We can divide by 3 for both the numerator and denominator. It's going to be negative 5 over 2, and that is negative 2.5. So that makes our y-intercept roughly there. So it's going to be 0, negative 2.5. Next we can check for our x-intercepts. And this is where y is going to be 0. So we're going to have 0 is equal to 5 times x minus 3 over 3 times x plus 2. So really we just care about the numerator here because that's going to be where the function is 0. So if we put in a value of x equal to 3, that's going to be 3 minus 3, and then this whole term will be 0. So we actually can get a x-intercept to be at 3, 0. Now that we have that 3, 0, we can put that down on the graph here and say that's 3, I'll put it actually above, 3, 0. And again, because we have this vertical asymptote and horizontal asymptote, as well as 2 points that this function has to go through, we know the function in this area is going to look something like that. It's going to approach the horizontal and vertical asymptote, but never touch them. Now we're going to do kind of the last step, which is to test a value that's to the left of the vertical asymptote. So in this case, we have negative 2, so I'm going to test a value of negative 3. So I'm going to say f of negative 3 is equal to 5 times negative 3 minus 3, and we're going to have 3, negative 3 plus 2. So this is going to be negative 6, so it's going to be negative 30 on top, divided by, and this is going to be negative 1 here, and then negative 3. So we're going to get a value of 10. And again, we have another point here, which is negative 3, 10. So if I go to our graph, we can say negative 3 is probably here, and 10 is probably up here. So we can have negative 3, 10. We now know that the graph looks something like that, and slopes up that way. Alright, so now we can move on to problem number 3. So for problem number 3, we have the function where we have a quadratic on top, that's 2x squared minus 3x plus 6 divided by x minus 2. So here we're going to go to step 1, factor the numerator and denominator if possible. So it might seem like this function on top here, this quadratic, right here is factorable, but if we do 2 times 6, that's going to give us 12. So we're trying to find factors that the product of them will equal 12, but also the sum of these factors adds up to -3. So if we list all the factors of 12, we have 1 and 12, 2 and 6, and 3 and 4. Now, because this 6 here, because this 2 and this 6 are positive, that means that the product has to be positive 12. So that are going to be 2 positive values or 2 negative values. So here, if we had 2 positives, it would be 13, and similarly it would be -13 if it was negative. And then we have 8 and -8. We have 7 and -7. So clearly none of these sums actually add up to -3. So this function on top, or this quadratic, is not factorable. So now we can move to problem or strategy tip number 2. So now we're going to go into the vertical asymptotes. And here we're going to get a vertical asymptote at x equal to 2. Now we've checked off that. Now we can go on to step number 3. So the horizontal asymptotes or oblique asymptotes. And in this case it's actually an oblique asymptote, and I can tell you why. So here we have a function where the degree in the numerator is exactly 1 higher than the degree on the denominator. So if we were to do x squared divided by x, we're going to get x, and that is a equation of a line that has a slope. It's not going to be like that horizontal or vertical asymptote. It's actually going to have a slope now. So we look at this function and we're going to realize, okay, well now there's going to be an oblique asymptote because this 2, the highest degree term in the numerator, which is 2 in this case, is exactly 1 higher than the highest degree term in the denominator. And the way we find an oblique asymptote is we use polynomial long division. So we're going to do 2x squared minus 3x plus 6, and this is all divided by x minus 2. So here I'm going to write 2x, and then 2x times x is going to be 2x squared minus 4x, and if I subtract all those, this is going to be 0. And then now we're subtracting -4, so we're adding 4. We're going to get x plus 6 if I bring that down. Now I'll do plus 1. And here it's going to be x minus 2. And again, we're subtracting a negative, so it's going to be 8. So there's a remainder 8. When we're doing this, we actually don't care about the remainder. We only care about the quotient here. So we don't care about the remainder. This is the equation of our oblique asymptote, or slanted asymptote. So now we can graph this. So if I go to 1, this is going to be the y-intercept here, and then it's going to have a slope of 2. So I'm going to draw a line that goes through this like that. And we'll say that is a slope of 2. We'll do that in blue. So that is our oblique asymptote. Okay, now we can move on to part number 4, or step number 4. We'll see if there's a y-intercept or an x-intercept. So here, if we do this function, I'll just write it down here. So now that we have the function, I can put in a x value of 0, which is going to give us the y-intercept. So 2 times 0 squared minus 3 times 0 plus 6 divided by 0 minus 2. So we're going to get a x-intercept of 6 over -2, y-intercept, and that will be at the point -3. So 0, -3. So if we go to 0, we're going to get a negative value for a point on our graph. So it's going to be around there. That is 0, -3. So in this situation, we actually don't have a x-intercept. It doesn't cross the x-axis. So now we can move to step number 5. So the value from the left of the vertical asymptote and from the right. So from the left, well, we already actually have a value from the left of the vertical asymptote. We have this 0, -3. So if we know that an asymptote is a line that the function is going to approach but never touch, we can basically write it as something like this, and then again it's going to kind of slope downwards like that. and that will be the shape of the function with this oblique asymptote and this horizontal asymptote, or vertical asymptote. So now I'm going to go to the right of this x equal to 2 value. So I'm going to put in an x value of 3. So we can go f of 3, and that's going to be 2 times 3 squared minus 3 times 3 plus 6. And we have 3 minus 2. So this is going to be, that's 9, that's 18 minus 9, that's 9 plus 6, so it's 15 over, and then 3 minus 2 is a 1. So we have f of 3 is equal to 15. So we get a point that's probably up here. And I know it's going to be above the oblique asymptote because I can just plug in f of 3 of our equation of our oblique asymptote, which is right here. So if I go for this line right here, y is equal to 2x plus 1. If I plug in a 3 for the x value, well, that's going to be 6, so y is going to equal 7. So I now know that my function is going to exist above this point because the value I got when I put in f of 3 was 15, and that was higher than the value I got when I plugged it into the oblique asymptote, which was 7. So now we can know that the graph is going to look something like this. Alright, so now I want to talk about how the organization of your environment actually can affect your cognitive performance. So a study done by researchers at Princeton University found that people performed poorly on cognitive tasks when the objects in their field of view were in disarray or were disorganized compared to when they were neatly arranged. This is why it's important to get in the habit of cleaning your environment or your area of study before doing homework or before even writing tests. Additionally, a similar study done by the Academic Journal of Behavior and Information Technology found that this cognitive decline was shown when people had a disorganized or cluttered desktop on their computer. So make sure that your virtual and real environment are clean and organized if you're wanting to perform at your best. Thank you for taking the time to watch this video. If you guys like this content, I'd really appreciate you liking the video and subscribing to the channel to see more videos just like this. I make a ton of content to help in high school math and physics, as well as improve the mindset of a student. If you guys have a specific topic you want me to cover, let me know in the comments below. Thanks again, and I'll see you guys in the next video.